Let us continue our discussion of computer organization subject and the prescribed textbook which we are using referring for the content as well as the diagrams is Carl V. Hamasher's textbook. We are into unit 5, and in the previous session we had discussed pipelining. So what was pipelining? The objective of pipelining was organizing in an effective way the hardware and the system so that concurrent activities are facilitated. So in pipelining, the basic crux is concurrent machine instruction execution. This these diagrams we had referred to understand the concept, and we had said there is a two-stage pipeline wherein we'll be having separate hardware for instruction fetch and execution as well as a buffer, interstage buffer. If it is a four-stage pipelining, we'll be using three buffers: buffer 1, buffer 2, buffer 3, and the instruction execution stages will be fetch, decode, execute, and write. We try to understand the role of cache memory, and then we ended with the word hazard. And what we said regarding hazard, uh, stalling of pipelining because of delays. That is a hazard. So, what are the kinds of hazards? You have data hazard, you have controller instruction hazard. So, data hazard indicates non availability of source and destination operands, while instruction or control hazard indicates delay in availability of instructions because of cache miss. So let us continue our discussion. Let us take this thread forward from pipelining to hazard, from hazard to data hazard. So today's topic under discussion will be data hazards. Today's topic under discussion will be data hazards. Let us continue our discussion. So we have understood the meaning of hazard, and we also now know what is a data hazard. Because of data hazard, what happens? Pipelining is stalled. Why pipelining is stalled? Because of non availability or delay in the availability of the data which is to be operated upon for execution. So let us continue our discussion. Uh, let us take these instructions. Let us assume that these are the two instructions. One is, in the first one we are performing addition, and in the second one we are performing multiplication. So the value of a is given as 5. So here first a will be revised to 3 plus 5 getting 8, and then b will be giving an output of 4 multiplied by 8, that is 32, if the execution is sequential. What is the meaning of sequential execution? First a instruction will be executed, then b will be calculated, the multiplication will be calculated. Let us assume for pipelining the instructions need to be operated upon concurrently. It means what? The addition and the multiplication operations are to be done concurrently. When they are being done concurrently, b may calculate multiplication of 4 multiplied by a by taking a's old value, not the latest value, as the operations are concurrent and the latest value available at this instant of time is 5 only. So this will be a wrong calculation. This will be a wrong calculation. So what is the takeaway from these two sequential and concurrent instruction execution comparisons? So if there is a dependency, then it is better to go for sequential execution. Better to go for sequential execution. Let us take another example. We are calculating multiplication uh, of 5 multiplied by c and keeping the result in a, as well as we are performing addition of 20 and c and keeping the result in B. You can see here that these instructions, if we call them as instruction 1 and instruction 2, there is no dependency among them. As there is no dependency among them, you can concurrently execute these two instructions. You can concurrently execute these two instructions. Let us take two more instructions to understand the meaning of stalling, the meaning of pipelining, the meaning of data hazard. What is the first instruction here? The first instruction is multiplication. What will be multiplied? R2 and R3 will be multiplied and the resultant will be kept in R4. Similarly, the next instruction is addition. Here, R5 and R4 are added and the result will be kept in R6. So, in the first multiply instruction, R2 and R3 are the source registers, while R4 is the destination register. But in addition instruction, second instruction, R5 and R4 are the source registers and R6 is the destination register. It means what? If we are trying to perform multiplication and addition concurrently, it may happen that while performing this addition and while decoding this, the add instruction comes to know that R4, there is a dependency on R4 and R4 is yet to be calculated. This kind of situation may occur. So the same thing, let us try to understand with the help of a diagram depicted below. See here, the first instruction is multiplication. The second instruction is addition. Okay, and in one clock burst, one instruction needs to be executed. It means in one clock burst, multiply will be executed. In one clock burst, addition will be executed. So, this multiplication instruction has steps of what? Fetch, decode, execute, and write. Fetch, decode, execute, and write. For instruction 1, multiplication. For instruction 1, multiplication. Now, assume that there is a concurrent execution started, concurrent processing started. Now at clock cycle 2, fetch operation is performed for addition. So fetch operation is performed for addition means what? Contents of register R5 and R4 are need to be brought, let us say. Now at clock cycle 3, what happens? D2, that is decode, happens. At decode, what is understood? We need R4 for executing this. We need R4 for executing this. But there is a dependency on of R4 calculation on the first instruction. So this dependency is depicted by this dotted line. So this dependency will cause the delay. This dependency will cause the delay till W1 of instruction 1 of multiplication is completed. Then only D2 decode will be started. That's why D2 is now depicted as D2A. Then E2, then W2 will be performed. As D2 is delayed, why D2 is delayed? Because it is waiting for W1. As D2 is delayed and it is finishing after clock cycle 5, so D3 will initiate only at 6 because D3 is dependent on D2. So this will lead to, because of this data dependency between D2 and W1, this will lead to stalling, and stalling uh, indicates pipeline hazard. Stalling indicates pipeline hazard. Here, the hazard type is a data hazard. The hazard type is a data hazard. The same discussion is given here. Let us try to correlate this discussion. Add instruction in cycle 3. So this is cycle 3. Okay. D2, while decoding, realizes that R4 is used as a source operand. R4 is used as a source operand. Hence, D2 has to wait for W1 to finish. That's why D2 is delayed till clock cycle 5, and that's why D2 is now denoted as D2A. Now D3 of I3 also needs to be delayed because it cannot proceed D2A. Hence this is stalling, hence this data hazard. Hence this data hazard. Now let us look at the next keyword. The next keyword is operand forwarding. What was the previous keyword which we have mentioned? The previous keyword was data hazard. Data hazard is pipeline stalling, delays. So there is a delay, there is a stalling, there is a halt in the pipelining process. This delay, this halt, this can be overcome. The data hazard can be overcome with the help of a mechanism called as operand forwarding. With the help of a mechanism called as operand forwarding. Let us try to understand that. Let us try to understand that with the help of the diagram. Okay, so this is the diagram here. This is the diagram here for operand forwarding. This is a diagram here for operand forwarding. What we are seeing here, these are our source 1 and source 2 registers. In this case, let us say R2, R4. Okay, this is the ALU. This is the ALU and this is the result. Now, the data forwarding path is depicted here after the result register, after the result register. Now, this, what is the meaning of this data forwarding or operand forwarding mechanism? Let us try to understand that. Okay, let us say I2 is an instruction waiting for W to finish. Okay, now in this case, I2 need not wait for W. There is an alternative method. What is that alternative method? The data is already available at the output of ALU. Okay, once the execute stage completes step E1, once the execute stage completes E1, hence this delay can be reduced, and this result of I can be forwarded directly to E2. The result of I can be forwarded directly to E2. So that's what is the meaning of operand forwarding. So let us try to understand this diagram also. There is an ALU, right? So that the ALU has two multiplexers. This is the ALU, these are the two multiplexers connected to the ALU. Okay, now instead of source 1 and source 2, we can get data from them. We can get data from them after completion of D2 in I2. Okay, what will happen is, as dependency is found out, we'll be bypassing the sources and we'll be performing operand forwarding, or we'll be performing data forwarding. Hence, R2, which is not having any dependency, is loaded in source 1 in clock cycle 3, while in result the product is already available that will be taken for by execute 2. Hence, this diagram explains operand forwarding, a mechanism to overcome data hazard in pipelining topic. Let us take a finish our discussion with a small point. Till now, data hazard was handled with the help of a hardware, with the help of the hardware. Now it can also be handled with the help of software. With the help of software means with the help of compiler. With the help of compiler means some special instructions for delay are kept in the compiler, as can be depicted here. NOP indicating no operations between instruction 1 and instruction 2 are inserted to take care of these delays, to take care of these delays. So if a compiler or a software is handling data hazard, then it is uh, beneficial in the sense we can have a simpler hardware. So with this, I am stopping the discussion of data hazard. Thank you.